So the first thing we're going to look at is the orders of reaction, which essentially is the magnitude to which the rate is affected by changing the concentration of a reactant. So for example, if you double the concentration of that reactant, does it double the rate? Does it quadruple the rate? Does the rate remain unchanged? And that is determined by the order of that reactant. So when we're talking about orders of reactants, what we're talking about is the extent to which the rate is affected, that's both increased or decreased, by any change in the concentration of a particular reactant. So there are three different orders that you need to know. We have zero order reactants, first order reactants, and second order reactants. So we'll start with zero order. So a zero order reactant is a reactant where changing the concentration of that reactant has no effect on the rate. So you can double it, quadruple it, you can halve it, it won't change the rate of the reaction. So the change in rate is effectively equal to the change in concentration to the power 0. Anything to the power 0 is 1. So the change in rate is equal to 1, so it doesn't change. So zero order reactants are reactants that when you change their concentration, there is no effect on the rate. And that is because the change in rate is proportional to the change in concentration to the power 0. First order reactants are when you change the concentration of that reactant and there is a directly proportional effect on the rate. So if I double the concentration, it doubles the rate. If I quadruple the concentration, it quadruples the rate. If I halve the concentration, it halves the rate. It has a directly proportional effect. And that is because the change in rate is equal to the change in concentration to the power of 1. So first order reactants can be identified because when you change their concentration, assuming everything else remains the same, then you'll get a directly proportional response to the change in rate. And then we have second order reactants where you get an exponential effect on the rate. And that is because the change in rate here is equal to the change in concentration squared. So you have an exponential effect. So if I were to double the concentration of a second order reactant, it would actually quadruple the rate because it would increase the rate by the change in concentration squared. If I doubled it, times it by 2, 2 squared is 4, so the rate would increase by 4. If I were to triple the concentration of a second order reactant, then the rate would increase by 3 squared, so it would increase by a factor of 9. So we have zero order reactants, no effect on the rate when you change their concentration. First order reactants have a directly proportional effect on the rate of reaction, and second order reactions have an exponential effect. So they're the three orders of reactants. The overall order of a reaction is determined just by the sum total of the individual orders of the reactants. So if I had two reactants, one of them was first order, one of them was second order, the overall order of reaction would be third order because you just add them up. If I had three reactants and all three of them were second order, then the overall order would be 6. So if you want to know the overall order of the reaction, you just add up the orders of the individual reactants. So to start with, you need to know what the orders are and what they represent. And we're going to talk about how you can actually work out what order a reactant is. And there's multiple different ways of doing this. And we're going to start off with the graphical determination of order. So by plotting concentration time graphs, we can identify the order of the reaction. So I've got 3 concentration time graphs here, different shapes, different effects on rate, and you can see clearly that the rate differs in all of these because the rate in a concentration time graph, the rate is represented by the gradient of the line, and you can see very clearly that the gradients are very different in these graphs. So the first thing is you can identify a zero order reactant from a concentration time graph because the rate, we should know in a zero order reaction, if I increase or decrease the concentration, the rate doesn't change. And in a concentration time graph, the rate is the gradient. So we can see here that that gradient is not changing. That rate is remaining constant. So we can say that this reactant, whatever it is, must be zero order. So zero order reactants can be identified if the concentration time graph is linear. Okay, so if we have a linear concentration time graph, then it must be a zero order reactant because the gradient isn't changing, therefore the rate isn't changing. Because if the gradient is constant, then so is rate. Now, the other thing we can do to prove this is we can plot a slightly different graph. We can plot a rate concentration graph. And rate concentration graphs are really useful for identifying order of reactant. So we can see here that as the concentration increases, the rate stays the same. So if you just did rise over run to work out the gradient of that line and then plotted it against concentration, what you get is a horizontal line like that. And very clearly we can see that as concentration is increasing, the rate is remaining constant. This is a zero order reactant. So this one here, this one is a first order reactant, and there are two ways of proving that from the graph. Now, number one is we're going to look at the relationship between the concentration and the time. So what you will notice is in a first order reaction, in a first order reactant, the half-life of the concentration is constant. So what I mean by that is if you look at the starting concentration and then the time taken for that concentration to halve, let's call that distance there x, and then you look at how long it took to halve again, and that is the same value, and then the time taken for that to halve again, and again it's the same amount of time. If you have a constant half-life, so it takes the same amount of time for the concentration to halve each time, then that's evidence of it being a first order reactant. So first order reactants can be identified from a concentration time graph if the half-life of concentration is constant. Okay, so if you've got a constant half-life, so it takes the exact same amount of time for the concentration to halve each time, then that is evidence of it being a first order reactant. Secondly, what you could do is you could plot a rate concentration graph. And how you would do that is you would need to take tangents at least minimum 3 different concentrations. Now we tend to start with the initial concentration, so you want to take a tangent right at the beginning. We'll take one sort of at the midpoint here, and then we'll take one a bit further down here. Okay, so if you just draw 3 tangents, now 3 tangents is all you need. If you do 3 tangents and you work out the gradient of each of these tangents, these 3 tangents, and then you plot them, what you will see, let's just have a quick think about what that's going to look like. So if we're looking at the shape of this, so the gradient is slowing down, so the rate is slowing. So at a high concentration the rate is high, and at a low concentration the rate is low, which is what you'd expect. So if you took these 3 gradients and worked out you took these 3 tangents and worked out the gradient of each one of those tangents and you plotted them, what you would find is a linear relationship. And again, if you remember the definition for a first order reactant, the change in concentration of a first order reactant has a directly proportional effect on the rate. So you would expect a linear relationship. So again, if we convert to a rate concentration graph for a 0 order reactant, we just get a horizontal line where the rate does not change with concentration. However, if we do that for a first order reactant, we get a linear correlation between concentration and rate that is directly proportional. We don't necessarily have to do this step if we can prove that the half-life of the concentration is constant, then that is enough to prove that it is first order. Finally, we have second order. Now, we can't determine that this is a second order reactant from the concentration time graph. It looks similar to a first order reactant, and we could look at the half-life to see if it was, and we'd find that the half-life is not constant for this. But eliminating the possibility of 0 order or first order isn't good enough. You need to actually confirm that it's second order. So the way we would do that is we would convert it to a rate concentration graph. So by taking tangents and plotting a rate concentration graph, we can identify a second order reactant. So we're going to do the same thing. In order to get from a concentration time graph to a rate concentration graph, you need to take at least 3 tangents. So again, I'm going to take one at the very beginning. The initial rate of reaction is what we want. We'd have one at about the midpoint, and again one closer to the end. So 3 tangents is all you're going to need. Again, use rise over run to calculate the gradient of each one of those lines, and then you can plot a new graph. Rate over concentration, and we can see that again the rate is starting off fast and getting slower, So this one's going to curve down. So if we have a curve, then we know that it is a second order reactant. Now, just to double check, just to prove that that is second order, what you would do, or what you could do, is plot rate against concentration squared, and if it was second order, you get a nice linear relationship. Okay, now don't worry too much about the direction that they're going. It just depends whether you're looking at a reactant or a product. What you're looking really for is the shape. If you just have this horizontal line, then you know it's zero order. If you have a directly proportional linear correlation, then you know it is first order. And if you have an exponential relationship between rate and concentration, then it is second order, which you can confirm by plotting rate against concentration squared, and that would then give you a linear correlation, which confirms that it is second order. So I'll just make a note of that, so you can confirm a second order reactant by plotting rate against concentration squared, which will give a linear relationship. Okay, so just to recap then, if we have a concentration time graph where the gradient does not change, that's a big indicator for it being a zero order reactant. If you plotted the rate against concentration, we would get this horizontal line where the rate does not change with the change in concentration, confirming it's zero order. A first order reactant, we can look at the concentration time graph. If the time taken for the concentration to halve is constant, then that is evidence for it being a first order reactant. We can also take at least 3 tangents, calculate the gradient of those tangents, and plot rate against concentration, because obviously the tangent of the line is the rate at that particular concentration. So you could then plot rate against concentration, and if you have a directly proportional linear relationship, then that shows that it is first order. And finally, if we have a second order reactant, then what we can do is we can look at take the gradients, the tangents and the gradients, and plot those, and they will, again, if you have an exponential relationship between rate and concentration, then it is second order. And just to confirm that it is second order, you can plot rate against concentration squared, and if you get a nice linear directly proportional relationship between rate and concentration squared, then you have proven that it is a second order reactant.